In this video, I'll talk about the Radiant Probability Calculator and linear functions of random variables that you already read about in Chapter 2 in the book. So let's start with an example with playing cards. Just for illustration purposes, we're interested in determining the probability of getting 9 red cards out of 15 draws from a deck that has no hearts. And note that we're drawing cards with a replacement. So this is an example very similar to one we talked about in class, where we wanted to establish the probability of getting 2 red cards out of 3 draws from this same deck. In that example, in class we established that we could get 2 reds out of 3 draws as follows: red, red, black, red, black, red, or black, red, red. What was the probability of getting a red out of this deck? It was 1/3, and the probability of not getting a red was 2/3. So here we establish the different ways we could get 2 out of 3, and we establish the probabilities. Now once we're talking about 9 reds out of 15, there's obviously more combinations, and so it's easy to either use a formula or something like the Radiant Probability Calculator. So let's take a look and see how we can establish that probability. Note that I'm clicking here on the help icon on the top right and then on help. It says version 341, so you'd need that version to follow along the examples. All right, what's the distribution of binomial? How many trials? 15. Right, we're doing 15 draws. The probability of drawing a red is 1/3. And we want to see what the probability of getting 9 reds. Okay, so those are the numbers I've put in. The number of trials, 15, the probability of success, 1/3, and the probability, the number of reds we're interested in. And what we get back is a plot that shows this bar here, the height of which tells us the probability of getting exactly 9 reds out of 15. That probability is also shown here. Okay, so probability of 2.2% getting 9 reds out of 15 draws. We get extra information as well. What's the probability of getting, for example, 9 or fewer reds out of 15 draws? And so that's a little over 99%. So very, very likely. So let's go back here. What are the calculations that are being done by Radiant under the hood? 2 components. Right? So our probability of interest that we set out to establish was the probability that our random variable x takes on a value of 9. Right? So 9 reds out of 15 draws. First we have to establish how many different ways can we get that. Can we get 9 reds out of 15? So the number of combinations is going to be n factorial, which in our case is 15, n factorial over x factorial, which is 9, 15 minus 9 factorial, right? So this is the number of combinations. We know our probabilities. Probability of a success, or in our case a red, is 1/3 to the power 9 times 1 minus 1/3 to the power 15 minus 9. Right, so that's the probability of getting exactly 9 reds. But the probability calculator also gave us the probability of x is smaller than or equal to 9, which might be convenient or interesting to know in some cases. So how does it establish that? Well, it takes this first probability, right, probability of x equal to 9, and then it adds to that the probability of x is equal to 8, probability that we're going to get 7 reds, plus the probability of getting 6 reds, and so on, all the way through to probability of getting no reds, adds those all up, and that's the probability of 9 or fewer reds out of 15 draws. So you probably don't want to do that by hand. You could consider doing it in Excel with lots of copy and pasting, but as I showed you in the probability calculator, those probabilities are automatically specified as soon as we tell tell the application, right? So base probability calculator, right? What the parameters of our distribution are. In this case, that was 15, right? Number of draws. Probability of a red is a third, and we specified a bound here. Okay. We'll get back to bounds in a little bit. All right, let's look at another example. Similar to something we also saw in class. So now you're organizing an outing to an NBA basketball game in LA. 200 people have been invited. Each person has a probability of showing up of 30%. And you have budget for 50 tickets. So is that going to be enough? First question then was the probability that too many people show up. Well, what would be too many? Well, if we buy 50, it'd be the probability of more than 50 showing up, right? Probability of, let's say, our random variable x more than 51 showing up. How do we establish that? Well, we've got our parameters, right? So it's another binomial. N is equal to 200. P is equal to 0.3. And we're going to establish what the probability is of more than 51. More than 50. My mistake. More than 50 people showing up. Let's take a look. Okay, so this is quite straightforward. We just specify parameters of our distribution. 200 people invited. Probability of each joining is 0.3. And now we have to specify, let's say that we buy 50 tickets. So what we're interested in is what's the probability that more than 50 people show up. Okay. So this blue bar here shows us the probability of exactly 50 people showing up. That plus everything to the left here is the probability of fewer than or equal to 50 people showing up. And the gray set here is more than 50 showing up. That's a sizable chunk of the density. In fact, it's 93% probability. Right, 93% of the total probability. So the chances that more people are going to show up than you can handle, right, more than 50, is very, very high. It's 93%. So that's probably not going to make anybody very happy, because you're going to have, quite likely, lots of people showing up that you don't have a ticket for. So maybe then you decide, well, you know what, I actually want 100% service level. Anybody that shows up, right, doesn't matter what, they're going to have a ticket. So I'm assuming you're going to figure out what the impact of that's going to be, the number of tickets you should get, but we can specify it. So our distribution hasn't changed. The only thing that's changed is we've now specified a probability. So before we put in a value and then it gives us back a probability. Now we're going to specify a probability, and it's going to tell us a value of how many tickets we should get to be able to achieve that service level of 100%. So what does it tell us? It tells us that we would actually need to get 200 tickets, which makes sense. If you want to make sure that anybody and everybody that shows up that you invited, that nobody's going to be left without a seat, then of course you need exactly 200 tickets in this case, right? Because only then do you have a 100% probability that everybody's going to have a seat. That's probably going to be expensive, right? You only have budget for 50 tickets now, and if you go ask for an increase in that budget to 200 tickets, it's probably not going to work very well. So what about trying for a 95% service level? Right, so a 5% chance of people showing up that don't have a seat. What do? We just specify, instead of 1, we specify 0.95, right? This is a probability that we're putting in, and it backs out for us what the boundary is, what the bound is in terms of the number of tickets we would need. The probability of exactly 71 people showing up is not very high, but the probability now of more than 71 people showing up is less than 5%. Okay, and so that tells us we have a service level in excess of 95%, which is exactly what we wanted. That's it. Pretty straightforward. Let's look at one more example. This is similar to what we talked about in class with respect to HP. We'll finish up that example in our next class. In Germany, demand on average, right, so the expected value is 4,200 printers, standard deviation of 2,200. In Switzerland, smaller demand, 420, and standard deviation of 200. What's the probability that the demand in Switzerland exceeds 900 units in a month? Okay. As I mentioned in class, the probability that we're working with here is a normal distribution, continuous. And so let's specify that in the probability calculator. What was the mean? The mean was 420 for Switzerland. The standard deviation was equal to 200. Okay, so this is the shape of the distribution. And we want to establish the probability of of demand being in excess of 900. Right? More than 900 printers being asked or being demanded in Switzerland. So we can specify a lower bound or an upper bound. Let me show you what things look like if we specify just the upper bound. It shows us an area to the left of 900, but what we were asking is the probability of more than 900 in demand. Right? So what's probably more convenient here is to specify a lower bound. In terms of the probability that are reported at the top, you probably already noticed that they're the same. And what we see if we specify a lower bound is the little area to the right of 900. Okay, if we specify 900 as an upper bound, we get the area to the left of 900, lower bound, the area to the right of 900. Okay, so this plot might be something that you would put in, say, a PowerPoint file or something to show management, say, hey, you know, the chances that we're going to get more than 900 demand are really very small. Look at this little area. What exactly is the size of that area? It's the span of that area. It's less than 1%. So less than 1% probability that you're going to get more than 900 units printers demanded in a particular month. Right, so that's the answer to the question. Let's see. What is the inventory level needed to achieve a 90% service level for Switzerland? So we won't have to change much here. The parameters of the distribution are the same. But now we're going to specify a probability. 90% surface level. So do you want an upper bound or a lower bound? Well, let's just put it in and see what happens. I like using the upper bound here because this tells me that the area to the left of this line here, that's 90%. Right? So this area is 90% of my total probability. And what we've done here, just like in the previous example, we specified a probability and it's backed out for us what the quantity is that goes with that, the number, the value. And it says the probability of getting fewer than 676.31 printers is equal to 90%. So how many printers should we stock if we want a 90% service level? That would probably be 677 units. Okay? Then we're going to have a service level just in excess of 90%. All right, last option. What's the probability that demand in Germany is between 500 and 1,000 units in a month? Well, Germany has a different probability distribution. It's normal too. It's normal as well, but it has some different parameters. Right? There's a lot more demand coming out of Germany. So the expected value or the mean is 4,200 and the standard deviation is 2,200. So it's a wider distribution. What we're interested in? We're interested in establishing the probability of demand in Germany falling in between 500 and 1,000. So the graph shows us that area. We'll see that it's not an overly big area here. And where's the probability? It's right here. Probability of between 500 and 1,000 units being demanded in a particular month is 2.7%. So there's a few examples for you to play around with. Try these out, see if you can figure out what's going on. Try using a lower bound or an upper bound. In either case, you'll get the same probabilities being shown in the summary component of the probability calculator. Right? So in this area here, same information will be shown, but the graph will look slightly different. And so depending on how you want to present it, you might prefer to have one or the other option. Okay, the next component I want to talk about is linear functions of random variables. So suppose we've already established the expected value of some random variable x. And now we want to establish the expected value of a times x. How would we do that? Do we have to calculate the expected value again, or can we do something more simple? Well, this equation here suggests that we can. So suppose that we have a random variable x, and we're going to multiply that thing by 2. We want to get the new expected value. We can actually just take the expected value that we perhaps already knew and multiply that times 2. Right? So these two are equivalent. Same thing with the variance. If we want to establish the variance of our random variable x multiplied by a factor a, then we can take that a out of the variance calculation, except here above we can just use 2. Here now we would have to use a square, or in this case 2 to the square, 2 to the power 2, a variance of x. Okay, so let's see what that would imply. We're back to the cafe example that we started on in class, that we worked on in class. And we have established and calculated the mean and standard deviation for hot drinks and cold drinks. The mean is 457 for hot drinks, 210 for cold drinks. We have the standard deviations over here. Okay, we have the standard deviations here. And we also know something about the extent to which these demands for hot and cold are related. So that was in units. Okay, these numbers are all in units, but we want to establish revenues. So how do we get from units to revenues? We multiply times the price. So we know that the price for hot beverages is $1.50, for cold beverages is $2.50. And so now we could either try to completely recalculate the different numbers, or we can use the numbers we already have for units and the formulas on the previous slide. And let's say we first want to establish the expected value of revenue for hot drinks. So it says here that's 1.5 times the number of hot drinks. And so how can we write that? It's going to be 1.5 times the expected value for hot drinks. And so that's 1.5 times 457, which is equal to 685.5. Okay, so we don't have to create a new variable per se, we don't have to do additional calculations, just we can take this multiplication factor outside of the expectation, multiply it out, and we get 685.5. Now, looking at the formula on the previous slide, variance of x, a squared times variance of x. How would we do these things here? So basically we have to go from the standard deviation to the variance first. Right? And so instead of times 1.5, we're going to have to use 1.5 squared times the variance of hot drinks. So how do we get from standard deviation to variance? We have to square. So the standard deviation for hot drinks is 244 squared. Okay, that's the variance. I'm going to take the square root of that thing. Now, this actually simplifies quite nicely to the following. 1.5 times 244.3. So basically what we can say is 1.5 times the standard deviation of hot is the number that we're looking at. And so that ends up being equal to 366.41. Okay, so let's do the same thing for cold beverages. 2.5, right? So the price for cold beverages. How do we get the expected value? 2.5 times the expected value of cold beverages in units. So that's equal to 2.5 times 210, which is equal to 525. What about the standard deviation? Again, on the previous slide, you see that the equation here would be 250 squared times the standard deviation squared, right, for our example in cold, but luckily that simplifies to 2.5 times the standard deviation of cold in units, and so that ends up being 300, well, let me just write this out. 2.5 times the standard deviation of cold is 145.6, which is equal to 364.09. Okay, so that should be reasonably straightforward, I hope. Things get a little more interesting once we have to talk about the sum of random variables. Okay, the expectation of a sum of random variables equals the sum of the expectations. What does it mean? If I want to get the expectation of a sum of random variables, we can actually just sum the expectations. There's some multiplication factors going on. We can take those out of the expectation just as we did before. And so that's going to be reasonably straightforward. If we want this expectation, so total revenue is what we're trying to establish across hot drinks and cold drinks. We can write that as 1.5 times expected value of hot drinks plus 2.5 expected value for cold drinks, which is going to be 1.5 times 457 plus 2.5 times 210, right? Whoops, 210. And so that ends up being equal to 1210.5. Now, what about the standard deviation of total revenues? Well, that takes a bit more work, and we're going to need a slightly adapted formula from the one we looked at previously. So with the expectations, right, you can just sum the expectations. For the variance, if the two variables are independent, so two random variables are independent, we can just sum them up, the variances. Or if we have some type of multiplication factor, we can take the a out of the multiplication factor out of the variance calculation. Just have to make sure we square it. That works if they're independent, but we already know from the data provided that they're not. Right, there's actually a correlation between these two variables. So if they're not independent, and we're looking at an equation like this, very similar to the one we just saw, except we have this extra component that's grafted on that takes into account that the variables are correlated. So this is the standard deviation of one of the random variables, standard deviation of the other, and then the correlation between the two. And we can expand this if there's some type of multiplication factor involved like here. And we can write this whole thing out and figure out the variance of the sum of these random variables, the variance of total revenues. So how would we do that? Let's see. That is going to be, we're first going to, instead of using the standard deviation, we now actually do have to write out the variance first. So it's going to be the variance of 1.5 times units in hot plus 2.5 cold units. And so that's going to be 1.5 squared, variance for hot, plus 2.5 squared times the variance for cold. That would be all if we were looking at two series that were independent. However, if they're not independent, then we have to add this extra component, which in our case would be 2 times 1.5, right? The price for a hot beverage times 2.5, price of a cold beverage, times the standard deviation for hot, which is 244.3, times the standard deviation for cold, which is 145.6, times the correlation between the two, which is minus 0.776. Okay, so this whole thing is what we're looking for. It's going to give us the variance of total revenues. And so let's write out the values there. It's going to be 1.5 squared times 44.3 squared. Where did that come from? It's the standard deviation for hot drinks. We have to square that. That's going to give us the variance for hot drinks. Plus 2.5 squared times 145.6 squared. That was the standard deviation of cold, right? We need to square that. And that would work if the two series are independent, but they're not. And then we have to add this component in, so let me just write that out one more time. 2 times 1.5 times 2.5 times 244.3. What was that again? Standard deviation for hot times 145.6 times the correlation. Okay, and that's going to give us the total variance for revenues, 62,372 and 25. So that's the variance. How do we get the standard deviation? Standard deviation, 1.5 hot plus 2.5 cold, going to be equal to the square root of that thing, 62,372.25, which is equal to 249.7. So it's a reasonably long formula. I will agree with you there. But once you know the numbers to plug in, it's not super bad. I want to show you a little example of how you could do this a little easier. Okay? I'll keep these for you. So let's load in some data. I'll show you an example. So in the screencast folder, I'm going to put this on Dropbox for you. Let's open up raincoats. So this is demand for raincoats in a department store and in an outlet store. And so we'd like to establish the revenues for this. Right? So these are that can't be fucking unit sales.